Okay, hello class. So this week's topic is based on atmospheric pressure and wind. So atmospheric pressure, also known as air pressure, so it's the force exerted by the weight of the atmosphere. So the gravitational pull of gases to the surface creates air pressure. So gas molecules have a higher density at the surface than higher altitudes, meaning that gas molecules have a higher pressure at the surface due to more weight of the atmosphere above it compared to the mountains that have a lower air pressure. So in this case, this is the standard atmospheric pressure profile. So this is taken from your lab manual. So we have altitude in one column and pressure on the other. So these pressure readings were taken by an instrument called a barometer, and this is just showing you that at 0 kilometers, so at ground level, the pressure is 1013.25, which is a high pressure system, compared to at 60 kilometers, which could be at the top of a mountain, and the pressure drops significantly at 0.203143. So the higher the barometric readings are taken, the lower the values. So what we just saw, which at 60 kilometers, there is a lower pressure. So this is an example question, not an example question, but this is one of your questions in your lab manuals. The highest peak in California is Mount Whitney. What is the average barometric pressure at the summit? So the average barometric pressure, you would look at this and convert it to kilometers, so 4 kilometers. So you'll get your value 616.402. So you would put that whole value as your answer. So that's how you'd answer those questions using this chart. So wind is the pressure gradient force. So the horizontal movement of air that results from differences in air pressure. So meaning that the difference from a high pressure system to a low pressure system. So the leading cause of this difference in pressure is temperature differences. So cool air sinks, which creates a high pressure system, and warm air rises, which creates a low pressure system. And wind always flows from high pressure to low pressure. So this is the movement of the wind. So another factor that influences wind is the Coriolis effect. So due to the rotation of Earth, objects moving over the surface are deflected to the right in the northern hemisphere, like this airplane, and to the left in the southern hemisphere, like this airplane. So when we get to this diagram, air in a high pressure system moves clockwise, and the air from the low pressure system moves counterclockwise and in the northern hemisphere, and it's reversed in the southern hemisphere. So air moves counterclockwise in a high pressure system, and air moves clockwise in a low pressure system. So in both high pressure systems, the air is moving out, and in the low pressure systems, the air is moving in. So high pressure, again, is always, the wind is always moving from the high to the low. So this is the global circulation model. So we're just going to refer to this diagram here. So we have 4 major pressure belts in both the southern hemisphere and the northern hemisphere, and they mirror each other, as you can see. So we have the equatorial low, and this is a thermal pressure system. So this means that the reason there is a low pressure is because of warm air. So the warm air is causing the air to rise, creating the equatorial low. And also we have the subtropical high pressure belt, and this is a dynamic pressure system. So meaning that there is mechanisms in the upper part of the atmosphere that is forcing the air to sink. So it's not associated with temperature, but it has a mechanism that's forcing it. And then we have the subpolar low, and it's a dynamic pressure system. So again, there is mechanisms that are allowing the air to rise, and it's not associated with temperature. And then we have the polar high pressure system and the polar high pressure belt. And this is a thermal pressure system. So the cool air causes the air to sink here. And then I'm going to mention the prevailing winds. So the four major prevailing winds are the northeast trade winds, found between 0 to 30 degrees latitude, and they blow from the northeast. And we have the southeast trade winds, which blows from the southeast, found between 0 to 30 degrees latitude. And then we have the westerlies blowing from the west, found between 30 degrees to 60 degrees, and again 30 degrees to 60 degrees in the northern hemisphere. And we have the polar easterlies blowing from the east, found between 90 degrees to 60 degrees. And again, it's not written here, but it's the polar easterlies, these blue arrows, from the east, 90 to 60 degrees. So the next concept is onshore and offshore breezes. So the main factor that you guys should know is that land heats up and cools more quickly than water. So in this scenario, this is an onshore breeze. So the island is heating up faster than the ocean. So this is causing a low pressure here. So warm air is rising, and there's a high pressure here. So we have the wind coming from the ocean, the cool air from the ocean, which creates a onshore breeze. And then at night, it's reversed. So the island is cooling faster than the ocean. So it creates a high pressure here. So cool air is sinking. So cool air is blowing from the land, which is creating an offshore breeze. And then we have the valley and mountain breezes. So this is the valley breeze example. So we have the sun warming up the mountain slope and part of the valley. So this is causing the overlying air to rise. So warm air is rising. And then we have the high pressure here, it's just sinking. So we have this valley breeze as the air is going up the slope and sinking back down. And then at night, the surface of the mountain is cooler than the valley floor, so this creates the cool air to sink, and this is bringing the air down, which causes a mountain breeze, and the warm air is rising. So this is the concepts for your lab, and if you have any questions, please visit me in office hours. So thank you for watching.